Okay, let's look at some Lewis dot structures. Questions from Alex. Let's look at this first one right here. It actually gives us a Lewis structure and asks us, is this Lewis structure reasonable? And it really asks us two questions. Is it reasonable? Click on yes. No, it has the wrong number of valence electrons. And what are the correct number of valence electrons? Or no, it has the right number of valence electrons but doesn't satisfy the octet rule. So let's look at this first. So nitrogen, this is N2, the molecule N2. So when we draw Lewis dot structures, the first thing we want to do is count the number of valence electrons that are in that molecule. So nitrogen is right here. It has 1, 2, 3, 4, 5 valence electrons. There's 2 of them, so this should have a total of 10 valence electrons altogether. So let's see if that first question is right. Does it have the right number of valence electrons? We have 2, 4, 6, 8, 10, 12. Okay, remember, each of those lines consists of 2 electrons that are being shared. So here's that first lone pair, so I'm going 2, 4, 6 for that line, 8 for that line, 10, 12. So this does not have the right number of valence electrons. The answer to that is no. The correct number is going to be 10. Let's check that. We should be right. And it turns out that we are right. So that's how you handle a problem like that. That's not too hard. Let's go to this second question that it's asking us. Draw the Lewis dot diagram for the Ge2+ cation. Okay, so this is germanium right here. So let's look at our periodic table. Okay, here's germanium right here. It has, let's count them, 1, 2, 3, 4 valence electrons is what germanium has. It has 4 valence electrons. Okay, so but it's lost 2 of them. So let's go and let's use Alex to draw this structure right here. I'm going to click on the atom symbol. I'm going to place germanium in there. Okay, it is an ion, so it's going to have a +2 in this case. And so let me get my dots here. I'm going to add a dot right there, and I'm going to add a dot right there. So I have the 2 of the 4 germanium electrons there, and it's going to be a 2+. So I'm going to add those brackets right there, and this is going to be a 2+, and that 2+. I'm going to check that, and again, that should be a correct structure. Okay, so there is the germanium cation, germanium 2+. Alright, let's keep going here. Draw the Lewis structure for ethane, C2H6. Alright, I'm going to just slip over here and see if we can't do this Lewis dot structure here. Okay, so C2H6, it is ethane that we have right here. So let me get a pen right here. Okay, so C2H6. Alright, so let's look at some of our rules. Remember some of our rules. The first thing we have to do is we have to count the number of valence electrons. Okay, so each carbon is going to have 4 valence electrons. When we look at that periodic table, that's what you'll find. I have 2 of them, so 4 times 2 is 8 valence electrons from the carbon. And each of the hydrogens have 6, so that's going to be +6 valence electrons. So 14 valence electrons is what I have to do. Okay, so we draw the bare atom first with single bonds. So there's carbon. There's my 2 carbons that are going to be bound together. Remember, hydrogens are always terminal. And so let me add my hydrogens around. I got 6 of them, so there's going to be 3 on this side. 1, 2, 3, and those are hydrogens. hydrogens. I'm going to have 6 or 3 over here. Okay, so there is my bare structure. Let me go ahead and count the electrons that I've used here. So there's 2, 4, 6, 8, 10, 12, 14. I've used all of them, so this is going to be my Lewis dot structure. Let's check for octets. So each hydrogen is going to have a duet. Looks like I'm accurate on those. Those all have duets. And there are 2, 4, 6, 8 around this carbon. There are 2, 4, 6, 8 valence electrons around that second carbon. So this looks to be a very, very valid Lewis dot structure. So let's go back then to Alex here. And let's go ahead and draw what we just did in Alex. A second. Okay. So let's go ahead and draw that carbon. Okay. Let's bond that to that second carbon. Okay, right there. So there's that second carbon. And then let's add those 6 hydrogens that we just drew. 1, 2, 3, 4, 5, 6. Let's go ahead and add those now. So grab that. So there is hydrogen, and there is my second hydrogen. There is my third hydrogen. There is my fourth hydrogen. There is my fifth hydrogen, and there is my 6th hydrogen right there. Okay, that is our Lewis dot structure that we did on the previous page. So I'm going to go ahead and submit that, and we should be in really good shape there. Okay, so let's do one more here. Let's do problem number 4. Draw the Lewis structure for hydrogen chloride molecule. Alright, let's go back here to this page. I got some room down here. Alright, Lewis dot structure for HCl, hydrogen chloride. Okay, so let's count the valence electrons. There is going to be 1 for hydrogen, as always, and chlorine is going to have, as you look at the periodic table, 7 valence electrons. If you're not sure how I got 7, come and find me and we'll talk about it. So this is going to have a total of 8 valence electrons. Okay, so I'm going to draw that H and bond it to the chlorine here. Alright, so I need to account for 8 valence electrons, and so far I have 2. So I need to add 6 more to this structure. Our rules would say start adding lone pairs to the outside terminal. Well, they're both terminal. Hydrogen already has its 2 that it's going to share right here, so I'm going to add those to the chlorine. There's 1, 2, 3, 4, 5, 6. So I got 2, 4, 6, 8. That is going to be fine. That is our Lewis dot structure right there for hydrogen chloride. Just check the octets. 2, 4, 6, 8 around the chlorine, and then hydrogen has its 2. So this is the correct Lewis dot structure for hydrogen chloride. And let's just go ahead and throw that into Alex here just to show you how I do it. There's going to be an H, add the bond. There's then going to be the Cl, and then we'll go ahead and take care of those lone pairs right there, and right there, and that should do it. We can go ahead and click check, and that should be a correct Lewis dot structure. And we probably have time for one more. Let's go ahead and add a 5th one here. Okay, draw the Lewis structure for phosphorus hexachloride, and it's going to be this ion right here. Okay, so let's go ahead and do that. Let's come over here. Let me just go ahead and add a new page here. Alright, so let me grab my marker and let's go ahead and do this. So it wants us to do phosphorus hexachloride, and that is a -1. I'm just going to double check just in case I forgot. So PCl6, and as I go back here, PCl6. Okay, so let's count the valence electrons. Phosphorus itself is right below nitrogen. It's going to have 5 valence electrons. Chlorine has 7 valence electrons, so that's going to be 7 times, there's 6 of them, 6. So there's 42 here, there's 5 here, and you have to account for this one right here. So that's going to be +1, and so that is going to equal then 48. So I have to count for 48. Alright, the second rule, we need to determine which one of these, the P or the Cl, is going to be the central atom. If you remember your electronegativity rules, the more electronegative goes on the outside. The less electronegative goes in the center of the molecule. So from our periodic table, we're going to find that phosphorus is less electronegative than chlorine. So I'm going to put that central. I'm going to draw my basic here, Cl, 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 3, 4, 5, 6. Okay, so it's not as even as I'd like it, but we'll just go. So far I've added 2, 4, 6, 8, 10, 12. I've added 12. Okay, so now I've got 36 left to put around there. Okay, so then we start adding lone pairs to the outside terminal atoms to form those octets. And so I've got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, so I've added lone pairs to each of those, and if we were to count those, then there are 2, 4, 6, 8 around each of those, and I've got 8 times 1, 2, 3, 4, 5, 6. 8 times 6 is 48. That is exactly how many I need to count for. Okay, so this is also going to be put into brackets since it's an ion, and it is going to have a -1 charge. So this is correct. Now as we check for octets here, we already know that each of the chlorines has an octet. Phosphorus does not have an octet. And this is one of those exceptions to the octet rule that we just have to keep in mind. And we'll talk more about this later, but as we move down in the periodic table, there are actually more orbitals available for these molecules, these atoms, to form molecules that have more than octets. This has 2, 4, 6, 8, 10, 12 surrounding that phosphorus. Alright, so this might be a little bit long. You can skip ahead to the end, but let's go ahead and throw this into Alex just to show that we're right. Okay, so again, I'm going to put that phosphorus right here in the middle, and I'm going to add bonds here. 1, 2, 3, 4. Wonder how we're going to. 5, 6. Alright, there is that, and then we're going to add chlorines as the terminal here, and then chlorine again as the terminal, and then the next chlorine here on the terminal, and I wish I could fast forward through this. Another chlorine right there on the terminal, another chlorine right there on the terminal, and the final chlorine right there on the terminal, and Okay, now we just need to go through, this is tedious, add your lone pairs. There's my lone pair around that one. There's my lone pair around this one. Lone pair around this guy. Lone pair here. Let's see where. Oops. Okay, lone pair right here. Lone pair right here. Okay, so there's that. Now remember, it's an ion, so we need to put it in those brackets. And that is a minus charge that we'll put up there. And so this should be a very correct Lewis dot structure for the phosphorus hexachloride ion. Go ahead and click on check. And let's hope we see green, and we do. So that's just some examples of Lewis dot structures. And again, just remember our algorithm for that. Count the valence electrons, determine the center atom, add the basic structure, and then add lone pairs to terminal ions as needed, and then start filling in octets. And that is how we do some Lewis dot structures.